All right, we are now recording. It is 9:33 on Monday, the 24th of April 2017. This is supposed to be Calculus 1 class. I have one student who's in and out a little bit, but he's back. And the others I hope will be coming. This is the last week in the term, which means all research papers are due this week.
Thursday
or
Wednesday.
Yes, of which this class has returned at none up till now, so please get those in. Unless you sent me some by email. I haven't checked those today to see if any have come in recently. You know about scholarships. It's EWI scholarship, Executive Women International. Its deadline is this coming Friday. So if you are going to get that one in, get it in now. And then the Financial Services Office has, I'm sure they have still the list of those for April. Most of those probably the deadlines are passed, but there's some that will be the end of the month. So those are still good, and soon they'll have, if they don't have it already, they'll have May's out there. Okay. Don't know of too much new stuff now, so let's just go on and get started on 4.5. And that's where we left off last time, so let's get set up from current slide. If it'll start from the slide, so far, there we go. I'll even turn on the projector and put my lights. I'll start at 48 minutes. Actually, what I was doing was grading papers because I had a few minutes between classes. So that's why I had that light on. Okay. By the way, the title of this section is L'Hopital's Rule. L'Hopital's Rule is named for the French mathematician Guillaume François Antoine Marquis de L'Hopital, okay, or something like that, okay. Lived in the late 1600s, early 1700s. He wrote the first textbook on calculus in 1696. And the name L'Hopital, it gives you how to pronounce that. Now, the reason I mention all that, he would be a potential paper topic, or how he went about finding this, and I think if you did pursue that line of thing, you would find there's a little bit of controversy here, okay? And I can't remember which one. There was a family of Bernoullis, okay? There were two brothers, I think, Johann and Jacob, and then either one or both of those had a bunch of sons, and one of those was Daniel, and there probably were others that were really good mathematicians and physicists, and they were a very competitive family. I think the two brothers got along okay, but they did compete with each other pretty rigorously. But then the fathers and sons even competed really rigorously, and one son snuck in an application on a prize that he knew his father was going for that same one, and when the son beat the father for the prize, the father kicked him out of the house. So it was some family dynamics going on there. Well, both of the fathers, the two brothers, were eminent mathematicians and physicists, and I think were both university professors, probably at different universities. And I don't know if one of those was in France or not, but L'Hopital attended and was a student of that Bernoulli. And supposedly, Bernoulli had come up with this rule, but had never published it. And L'Hopital, like it says here, wrote the first book of calculus, using a lot of stuff that he had learned from Professor Bernoulli. And because the other hadn't been, this particular rule, Bernoulli hadn't published, this was the first time it showed up in print, and everybody started calling it his rule, and really hacked off the elder Bernoulli, okay? There's a story in there somewhere, but I don't remember all the details, but anyway, that's yet another thing, and I was given for Christmas a book of 1001 quotes and then the backgrounds. I'm almost through with it, and it's just amazing how many things get attributed to somebody because either that's the first person they heard it from, even though that person may have been saying something he had heard from someone else, he or she had heard from someone else, and so it gets said to be his or hers when it really belonged to somebody else. So same thing here. L'Hopital's rule probably wasn't developed by L'Hopital. More than likely was a Bernoulli or someone else. So what L'Hopital's rule is, I've got other stories on that too. They're silly, but I probably don't need to take class time to do them. Okay. It's a valuable tool for computing certain limits, not all, but certain limits that are otherwise difficult to evaluate. That's also for determining asymptotic behavior, that's limits at infinity, and it says we'll use it for graph sketching in the next section, which I don't know if we'll have time to go there, but if we do, we'll do. So let's say we have a, I'll write it here before I do. Better get my pen reactivated in dark. Okay. We have a limit of a quotient. Excuse me? Yes. Right.
Okay.
Okay.
How you doing?
Okay,
I
good.
didn't catch my breath.
Okay.
Oh, did some walking?
I don't have the third test up here with me because that's later. Do you want it? Do you need it right now?
If you have it, I can get it. You need me to wait?
What's
Come
that?
back- You need me to come back by?
I hate for you to have to do that.
Okay.
Do you mind if I run down? Let me pause my recording here. Here's what we've got. Limit of a quotient. As x approaches a of alpha of x over g of x. Okay. Now, if you had something like this, especially when you're dividing things can get a little complicated at times. Now, the limit is f of x divided by g of x as x is approaching a, especially if g of a was 0. Then that would be it would either be undefined or it could be indeterminate. Okay? If it's undefined, there's no limit to it. If it's indeterminate, there may or may not be a limit to it. But it's going to be really hard to tell when you just can't plug in the x equal a because that gives you 0 in the denominator. So, L'Hopital's rule gives you a way for determining that limit, even though it may be almost impossible to do it just in that form. Okay? Roughly speaking, L'Hopital's rules state that when f of x divided by g of x has an indeterminate form of the type 0 over 0. Now, if it's 0 over 7, that's going to be 0. You don't need L'Hopital's rule. If it's 7 over 0, nothing's going to work. That's an undefined term. But if it's 0 over 0, you don't know. It's indeterminate. Or infinity over infinity. In other words, when you plug in x equal a to both the f and the g, you get infinite values. Well, which infinite wins? Okay, infinitely positive, infinitely negative. Does one cancel the other out? I mean, you can't cancel out infinities, but that's the deal. Okay, at x equal a, then we can replace the f of the ratio f of x to g of x by the quotient of the derivatives, f prime divided by g prime, and see what that gives you. Okay? So here is L'Hopital's rule. Zoomed in. Basically what I just said, but now a little more formally stated. assume that f of x and g of x are differentiable. Surely that's got to be the case, otherwise you can't use L'Hopital's rule. So both of those have to be differentiable functions on some open interval containing some value a, such that f of a is equal to g of a, and both of those are equal to 0. Okay? Now, also assume that g prime of x is not equal to 0, except possibly at a, okay? But not 0 everywhere, okay? Then the limit as x approaches a of f of x over g of x, as long as when you plug in at a is going to be a 0 in both cases, then take a derivative of both of those and then take the limit as x approaches a of the derivatives here. Now, if f prime turns out to be not 0 there, and g prime does, then the limit doesn't exist, because that's undefined. If f prime does turn out to be 0, but g prime isn't, then the limit does exist at 0. Or if f prime is something other than 0, and g prime is also something other than 0, then whatever they are, the ratio, that's the limit of the first one. Pretty nifty. It's pretty amazing that it works. If the limit on the right exists, or is infinite, positive or negative infinity, and that would mean that it's undefined. Okay, that's what it would be. It's either going to exist, or it would be, or it won't exist. Okay. This conclusion also holds as alpha of x and g of x are differentiable for x near but not equal to a, and that the limit as x approaches a of alpha of x is equal to plus or minus infinity, and the limit as x approaches a of g of x is plus or minus infinity. And that, then you do the same thing, take derivatives and see if you lose the infinities. Okay? And if you do, then you got it. If you lose one and gain and keep the other, then the limit doesn't exist. Furthermore, this rule is valid for one-sided limits. So this will work even if x is approaching a from one side has a value, but not from the other. You can still use it. So it's really a handy tool.
Does this only apply to the first derivative, or can you...
Okay. If that ratio of derivatives is also 0, 0, or infinity over infinity, blah, blah, yeah, then if it fits that criteria, then do it again. Because those are just two functions. They just happen to be derivatives. Just keep doing it until you either get something that's not defined or something it is. Okay. And then you'll know. So let's do example 1. Use L'Hopital's rule to evaluate this. I don't know where that function doesn't show up until example 6 or 7. So is it better to use, I'll just use a slide even though it's not appropriate for it. The limit as x approaches 2 of x cubed minus 8 over x fourth plus 2x minus 20. Now, if we weren't in L'Hopital's rule section and we just said find that limit, what would you do?
Do the loading, highlighting, hiding
No,
loading?
no, you're not taking derivative yet.
Okay. Well,
You're-
you would try to take out what you could.
Okay.
And
Okay. You
Oh,
plug it in, plug it in.
yeah.
Yeah, okay. So what happens if you plug in a 2 here?
you get 8 minus 8, 0.
0. No problem having 0 in the numerator.
Right.
Okay? But either your answer to the limit is going to be 0 or it's going to be indeterminate. Let's see what your denominator is.
That's 16
Right?
plus 4, which is 20, minus 20, 0.
0. Okay, so now we have an indeterminate form. Can't take that limit the regular way. Now, what you might try, I know we can factor this. I don't know how to factor that.
So we'd have to end up having to use what, the quadratic formula for that?
Not really, because it's not a 2, it's a 4.
Yeah.
Okay.
Right.
So what you would have to use is rational zeros test. The Descartes' rule of sines, synthetic division, and you may or may not get an answer. Okay? But L'Hopital's rule is much, because this is meets the criteria, you get an indeterminate form, 0 over 0, so just do L'Hopital's rule. But now it's not taking the derivative of the quotient, it's taking the derivative of the numerator and the numerator. So no low-de highs in here. Okay. So this would be, by L'Hopital's rule, the same as the limit, same limit, x approaching 2, of what would be your new
3x squared.
3x squared, and that's all for the numerator.
And then 4x
cubed
plus 2.
plus 2. Okay? How would you do that?
Plug it back in.
And what do you get?
For 12 over.
Okay, as soon as you get to 12, you know this is either going to have a limit or it's not going to have a limit. You're not going to do L'Hopital's rule again, because L'Hopital's rule does not work for 12s in the numerator, only for zeros or infinities.
Right.
So you're going to get some answer. Let's see what you get.
12, 8, 24 plus 2, 26.
Okay.
26.
So what does that?
Reduce down to what's
12 over 26, is that what you said?
Yes.
Okay, and that would be?
6 over 12, and then 13, excuse me.
Okay, 6 over 13. That's your limit. Never would have guessed it looking at the first.
Right.
But L'Hopital's rule gives it to you for the second, if I had done it right.
Did we do something wrong?
Yes.
Oh, no.
Right.
I think I messed up.
I listened to you. That's what I did wrong. Okay. No, I'm just kidding.
Right.
8 times 4 is
Sorry. 32
plus 2
plus
is
2, 34.
34.
And then 17.
17. Yeah, that's it. No problem. Never would have guessed that looking at that original. Okay? And frankly, I don't think there's any way you could have factored that to come up with that either. L'Hopital's rule, pretty straightforward. A very complicated looking thing, and you get a strange but true limit. Okay?
Convenient.
Let's do example 2. Find the limit as x approaches 2. They like that, don't they? Of 4 minus, I can't write,
Well, I hate how they-
x squared over sine of pi x. Okay. Can you plug it in, plug it in?
We'll try.
And what do you get?
16 over.
Wait, no, that's 4 minus. My minus
Oh, 4
is
minus. So
very
0 over.
okay.
Sine of what pi has?
No.
That's what it is. Or no, sine of 2 pi.
2 pi. And what's sine of 2 pi?
0.
0. 0 over 0. Can't do it. Can't determine it. Indeterminate form. So what do we do? Of each. Okay.
Numerator and denominator.
Right. And the derivative of the numerator would be
Dx.
minus 2x.
Oh,
Yeah.
I'm sorry again.
I know you can't see that. Yeah, sorry.
Minus 2x.
Over.
What, cosine?
Okay. Cosine of pi x
X, yeah.
times chain rule.
That's right. Negative times. Is it not?
Pi.
Okay, pi.
You take the derivative of the sine is cosine of pi x. That's
And then
exactly
whatever.
right. Then the derivative of the internal function,
That's right.
derivative of pi x is just pi.
Gotcha.
Put it in front though. It gets awkward putting it behind. Okay, now we try it again. And what would this give us?
Negative 4.
-4 is the numerator, and
I'm not sure.
yes, you are.
Put 2 back in.
Mm-hmm.
Cosine of, what is that? 4 pi?
No, it's 2 pi.
2, okay. 2 pi, or 3 pi?
No, it's 2 pi.
What
Okay,
about
it's
the
this
front?
times that.
Oh, okay. So you
The only place you have an x is cosine pi x. So plug in x equal to there and only there.
Okay. Which would give you 2 pi.
No.
No.
Cosine.
That'd be 1.
1.
Yep.
1 times pi is pi. There's what you get. -4 over pi. Very good. And that's what they got. They got it right this time. Okay. Now, example 3. Evaluate this. The limit as x approaches pi halves of cosine squared x over 1 minus sine x. If you tried to plug it in, what would you get?
0 over 0.
Yeah, cosine of pi halves is 0, and that squared is 0, and 1 minus sine of pi halves is 1, 1 minus 1 is 0. Yeah, but I'm not going to give you anything useful, so we try. Okay. And you're still approaching pi halves of.
Is that going to be negative sign?
You're going to have a negative sign in it.
But you take, so would you put an x in front?
Not an x in front.
2?
A 2 in front.
Okay, 2 sign that, okay.
That's not all.
Okay. Plus cosine?
No, not plus. Cosine x.
Okay.
Okay. Now let's back off and see. This is a composite function. It's a squaring function is the outer function.
Right.
The inner function is cosine x.
Gotcha.
Okay? So you do the outer function first, 2 times cosine x.
Right, which is negative, right,
2 times cosine x times the
inside.
derivative of the inside. And the inside is cosine x, and the derivative of cosine x is minus sine x. So, yeah, that is what you would get. You might not would have written it that way if you said it that way, but that is what you get. Okay? That's your numerator. Divided by
Just cosine x?
with the minus sign.
Or negative cosine x, right.
Okay, minus cosine x. Now, on this one, okay, before I didn't stop and do any more of saying, do you have any common factors? Because it was pretty clear you didn't. But this one, you didn't to begin with here until you look here and say, wait, there is a common factor here.
Cosine x.
Cosine x. So you can divide those out.
Okay.
But, yeah, so let's do that, okay? And the minuses divide out, and what do you get then?
Just sine x over 1.
Okay? Except for you got a 2 right there.
Right.
2.
Sorry.
And what's the limit of, as x approaches pi halves of sine x?
Let's see, pi halves get you 1.
Yeah?
And then, so 2.
Yes, that limit is 2.
Over 1, and just
Yeah,
2.
just 2. Now, there was another way to do this problem, okay? Because we know cosine squared x has an identity, doesn't it?
Yeah, I think it is the very first. What is it? Shoot, I remember us using this. Yeah, 1 plus cosine 2x over 2. Is that
Okay,
it?
that is one. That's not a useful one here, though.
Okay.
Simpler than that.
Oh, is it this one? Is it cosine 2x minus sine 2x equals 2 cosine?
Okay, yeah,
x?
that's basically the same one you were doing before.
Okay.
Let's not use a double angle anywhere. Yeah.
I know I've seen it before.
I know you have too, and I'm going to kick you when I tell you. You're ignoring the simplest one. And it does actually write it, but you can get it from what it is written. Go fundamental identities, right at the top, first one.
Oh, sine squared theta plus cosine squared theta equals 1.
That's our Pythagorean identity, the major one. That's always true.
You could move the sine x to the new
Okay,
one.
wait, yeah.
Oh.
Yeah, wait, no. Look at that identity. Solve for cosine squared. That would be 1 minus sine squared, wouldn't it?
Right.
Okay, let's start there. 1 minus sine squared x. Now that is also what?
Oh, I was just, I'm sorry, I'm
Yeah.
following along with you. So,
Okay.
You could divide out with that.
No, not yet.
Okay.
That's a difference of two perfect squares, isn't it? Can you factor that?
Yes.
How?
Sine x.
1 plus sine
plus
x
yeah.
times
1 minus sine x.
minus sine x. You got it.
Now
You can divide those two out, and what do you get?
1 plus sine x squared, which would be 2.
1 plus 1 is 2. The limit of that would be
2.
I wrote 1. Yuck! 2. Okay. Yeah. 1 plus, yeah. The limit of that, if I'd written my limit up there, that would be 2. So it gives the same way.
Gotcha.
And I don't know. This was basically a two-step problem, and then stuff. This was really just taking the derivative. It was just a one-step thing. It's a chain rule, but it's one step. So I think this is a little easier to do this way, but you didn't have to. It just shows you did get the right answer.
Right.
Okay. So the limit does exist, and that's equal to 2. Okay. Now, there was another way to do it too. I'm not suggesting it, but I was just going to say there is. If you didn't divide out the cosines, this thing is still 0 or 0.
So
You could do it one more time. Let's see what happens if you do.
So it'd be is that just
It's a product rule.
right? So
So-
derivative first times
Okay.
the second, or the
Okay,
first
what does that?
times the derivative of the second.
Right. So that's
2
going to be a
x,
sine, 2 sine x.
and then minus sine x.
Yeah, so that'll be 2.
2 right, and then second. So cosine x.
So it's going to be a plus, yeah. And it has a 2 there still.
Right, and then
Cosine x.
And then derivative first is just plus cosine x plus 2 cosine x.
Yeah. Okay, wait. Okay. Sorry. As you said, it's the derivative of the, it's the first times derivative of the second that
Right.
gives you this one.
Mm-hmm.
Plus the second
Yes,
times
cosine
derivative of
x.
the first.
Yes,
Derivative of sine is
cosine.
cosine, so it'd be 2
2
cosine
cosine.
times cosine,
Right,
2 cosine squared.
got it.
Okay. Over.
So just sine x plus sine x.
Minus.
Minus sine, that's right, cosine, yeah.
Okay, minus sine x, if x were right. Okay. Now, let's try plugging that in. And what do we get?
Let's see. Negative sine.
Okay. Let's plug in that.
Gotcha. That'd be 1.
That'd be,
Correct. 1 and then minus 2. So,
so this is
negative
minus 2. This
plus
would be
0.
a 0.
Mhm.
So minus 2 over
Negative 1.
minus 1 would be
Just positive 2.
2. Yeah. So you could do it that way too without dividing out anything.
Right.
See, this way involved dividing out. That way involved dividing out. This one you avoided dividing out anything, you still get it. Okay. Yeah.
I
So,
like that there's, different ways of
Yeah.
getting around it.
all roads lead to Rome, or something
Right,
like that.
yeah.
Okay. All right, that was example 3. I think I'll need to clean the page here. We'll move on to example 4. Now, they mention 0, 0, and infinity over infinity. Here's another form, 0 times infinity. Okay? And there's nothing in the thing there that says that would indicate this would work too, but let's just take a look at it. Evaluate this limit. The limit as x approaches 0, only from the positive side. Remember the rule said you can use this for one-sided limits, so we are going to use that here, of x log x. And why is that 0 from the plus required there?
See, because x log, I've seen the derivative of this before.
Okay. Yeah, well, forget about the x now. X is good anywhere.
Right.
They go to pressure from left or left.
Is it
Left,
the log
right.
of 0?
The log of 0 is not defined, so that's one of our problems.
Right.
But what's worse than that, log of a negative number is never defined either. So you have to be approaching x from the positive side because it can't even go over here.
Gotcha.
So that's why it has to be this. Now, this is a product here, and L'Hopital's rule didn't say anything about products, it only said quotients. But what you could have done is written this as log x over 1 over x. And then you would have had an infinity in the numerator, negative infinity in the numerator, because as x approaches 0 from the left, log x is going to negative infinity, and from the right, and x would be a positive infinity. 1 over x would be 1 over 0 would be going to positive infinity there too. So it'd be a negative infinity over positive infinity that does work. Okay. So that indeed is how you have to begin. Okay. You can't really do anything from this perspective. You have to rewrite it as the limit, because L'Hopital's rule only deals with quotients. As x approaches 0 from the plus side of log x over 1 over x. That is an ugly x, isn't it? My pen does not seem to be synchronized too well, because when I go to write it, it writes somewhere else. So let's see if I can. There, that's a little better. Okay. Now, and like I said, that is an indeterminate form, because as x approaches 0 from the positive side, log x is going to negative infinity. As x approaches 0 from the positive side, 1 over x is going to positive infinity. Who wins? Okay, we don't know. Okay, and it's a ratio anyway. So guess what we can do? Take a derivative of top and bottom. That would be x approaches 0 from the plus. I have to keep that. And what's the derivative of log x?
Is that x log?
No.
No.
Yeah, you're doing the derivative of that thing. Okay, and that would have started that way. Just the derivative of log x.
I'm not sure.
1 over x. Okay? Now, what's the derivative of... Okay, now, I wrote it that way. It would have been better to write it this way, taking a derivative. What's the derivative of that?
It'd just be 1. It'd be, excuse me, what, -1
Right?
to the -2?
You got it. Okay? And then, that might be easier to evaluate if you wrote it as minus 1 over x squared. Okay? Yeah, because that's a minus 2. Sorry. Write that in. Okay? Now, let's take a look at that. What is that? 1 over x over a negative 1 over x times 1 over x. That's 1 over x squared, right?
Exactly.
And one of these can cancel out. And then what's the limit as x approaches 0 from the right-hand side of 1 over x?
So you plug in a value that's to the right. Is that correct?
Yeah.
So you can plug in what, 1? Positive 1?
Okay, you could, and that would give you a 1
Negative.
down there. Then get closer, and if you put in a 1/2, that would give you a -2.
-2, right.
1/3 would be a -3, a 1/4 would be a -4, a 1/5 would be a -5. As you get closer and closer, this thing is going bigger and bigger. Well, let's wait. Pause a moment there, and just look at this form. This now is 1 over -1 over x, which is 1 divided by a -1 over x, which is 1 times a -x, right? And that would be, if that's a time sign, okay, hey, and that would be a -x.
Right.
Okay, now you plug in 0 there, and what do you get?
0 would be 0.
Scenarios here.
Or any value.
Yeah.
Positive, yeah.
That gives you 0. Okay? So that limit should be 0. Okay? I'm trying to find it here. Yep, that's exactly what we get. Okay. Where we are is section 4.5 on page 225 if you've got your book with you. It's L'Hôpital's rule. And you'll sort of have to go back and listen to the first part to get what you're doing, but we're going to do a few more examples and you'll see how this works. So I guess I'll wait and do that. Let me do say this though. Remember your research paper is due this week. Okay. What's that? Okay, it does. Okay, here's my. I always get asked this question, so here's my standard answer. If you email it, I will accept the email, yeah, for sure. But if you email it to me, whatever prints out when I open it and print it, that's what I have to grade. And I've had students who have sent me things that I don't know if the email screwed it up when it loaded it, or it was screwed up to begin with, but I think if they would have printed it, they'd say, oh, that's not what I want to give him, because just for example, I've had some that left their center, what do they call it? Justification. Center justification in throughout the paper, and that's not standard. They did it for the title, and then they never changed it as they went on, and they didn't pay attention, or else the thing messed up. So if you're confident that you got it in the format you want me to have it, you can send it to me. But if you're going to print it out anyway, and you want to give it to me that way, you can. I'll accept it either way, but I grade what I get. Whether you give it to me or you email it to me, when I print it out, that's what I got to grade. Okay, so yeah, absolutely. All right. So what we're going to do, we're on page, like I said, 225. We're on example 5 now. So I think we'll start over with L'Hôpital's rule and walk your way through this. I'm sorry, hit the wrong key.
And this example is going to answer my question about using it twice.
Yes, exactly. Though we already used it twice in
Right.
example, what, 1, wasn't it?
I think it was, yeah.
I think we did it. No, if it wasn't once, it was somewhere. Oh, when we did example 3 the other way, one way. Yeah. Okay. So yeah, we'd already, but this is that. Here's to evaluate a limit. Don't you love them? Actually, L'Hôpital's rule actually almost makes them fun. I never says that about limits, okay? Yeah. The limit as x approaches 0 of e to the x minus 1 over cosine x minus 1. Okay. Now that definitely is a transcendental ratio of functions. I mean, it's a ratio of transcendental functions. These are not anything that you can do for factoring or anything else. Those are functions not even very well related to one another. Now, what L'Hopital's rule is, okay, bounce back to the concept of limit. When you want to take a limit, one thing you could do is plug it in and see if it works. Okay, so let's plug in. E to the 0 is 1, minus 0 is
0.
Okay,
It's still
yeah, so it's still 1, and 1 minus 1 is
0.
0. Okay? Now, it's looking like the limit of this could either be 0 or indeterminate. Okay? Because you've got a 0 in the numerator. So only two options you have there. So let's do the denominator. Cosine of 0 is 1. Minus 1 is 0. So this is one of those indeterminate forms, 0 over 0. Like I said, before when we had these, we tried mathematical algebraic manipulations to see if we could clear those. And hang it up, Jack. There's nothing you're going to do with these two functions the way they are to do it. So now we call the L'Hopital's rule, which is much more fun than doing those other things anyway. And L'Hopital's rule says if you have one of those forms that's indeterminate, 0 over 0, or even a plus or minus infinity over plus or minus infinity. Either one of those, L'Hopital's rule works, and here's what L'Hopital's rule says to do. Take the derivative of the numerator, take the derivative of the denominator, try it again. Okay? So what we're going to do is write down the limit again. L'Hopital's rule says this is true. The limit as x approaches 0, and you give me the limit of the numerator. E to the x minus 1 over negative sine x. You got it. Okay? Now we take the limit of that. Plug it in, plug it in. E to the 0 is? Minus 1 is?
0.
Okay, and in the denominator?
0.
0 again. Still indeterminate. Guess what? That's still a ratio of two functions. Both of them are differentiable. Take the derivative again. So this will be the limit as x approaches 0 of e to the x over negative cosine x. And when you plug those in, what do you get? 1 over what?
Is that
negative 1, which is negative 1. There's your limit. And sure enough, that's what we got. And all of those were pretty easy steps, weren't they? There's L'Hopital's rule. Can really get you out of some messy derivatives. Limits. Okay, get you out of the limits. Okay?
Can you use L'Hopital's rule and then get to a position to where you use another rule?
Yeah. For instance, the one that we did earlier that, well, actually we could have started with the other one and never even used L'Hopital. I don't know, did we wind up using it just once? Or where you got to, remember the one that wound up with the cosine numerator, cosine denominator, we canceled that out. So that was, yeah.
Gotcha.
You get it down to a point that you can use something else and then use it, yeah. If it's easier than L'Hopital's rule again. All right. So L'Hopital's rule, very powerful little thing. And as Richard and I were talking before, L'Hopital, there's lots of evidence, and the fury that happened at the time we gave credence to it. L'Hopital got credit for this rule, even though he didn't come up with it, because his, you might say his major professor came up with it. The guy who taught him calculus taught him the rule, and because L'Hopital wrote the first book on calculus, he included the rule in it because it was so useful, and then everybody else said, wow, we've never heard of this before. What L'Hopital found here? But L'Hopital didn't find it. He was writing what he had learned from his professor, so he got credit for it, whereas it really was his professor's rule, but his professor had never published it, so L'Hopital got credit for it. And boy, did his professor blow his stack. Okay, so, but they never changed it and made it Bernoulli's rule. They kept it L'Hopital's rule.
That's crazy.
It was.
I think it's crazier to think though that the professor never
Right.
published it. Because
Right.
I mean, if you had a major breakthrough like that and
Right.
made it easier, why wouldn't you? You know?
Yeah. Well, to him, it's just a technique. You know, it wasn't. He probably didn't think of it as anything. This is just how he solved problems.
Yeah.
And he didn't think, oh, nobody else knows this?
Right.
You know? Does everybody know this? You know?
Exactly.
And the answer was no, they didn't. All right. All right. Let's do example 6. What if we want to find the limit as x approaches 1 of x squared plus 1 over 2x plus 1? Okay? How would you go about doing that?
Would you try plugging it in first?
Absolutely. And what happens?
You get 1 over.
Nope. If I wrote it
Oh,
right.
excuse me, 2
Yeah.
over 3.
2 over 3. Just because you have some complicated looking thing, don't say, oh, I'm going to use L'Hopital's rule and make it simpler. Because if you tried that, you're going to get a wrong answer. Because L'Hopital's rule requires that it be a form of 0 over 0 or infinity over infinity. This is not. Plug it in, plug it in. If you get an answer, you got the answer. Don't say, oh, this is too complicated. Let me use L'Hopital's rule and simplify it. If you did that, what would happen? If you use L'Hopital's rule
See, 2x
over
2.
2, and
And
that would be
then plug it back in, so just 2.
2. You get 2, which is the wrong answer.
Right.
Because you can't use L'Hopital's rule if it doesn't fit the criteria. The criteria is the numerator and denominator both must be zeros or an infinity.
Wow.
So
That
don't
can give-
use it. Yeah.
I can give you just a answer way off base.
Way, way off base.
Huh.
And because it is required that they be either 0 or an infinity. So don't do it if you don't need it. Okay.
Always plug it in first.
Yeah. All right. Now, here's another form which is a bit bizarre. I think we saw one which basically wound up being, I erased the wrong, I picked the wrong thing. Okay, now I got to go back and do that. Okay, I'm back. The earlier one we did was a form that was 0 times infinity, which by rewriting it, you got infinity over infinity or 0 over 0. But this form, evaluate this one. The limit as x approaches 0 of 1 minus sine x minus 1 over x. Okay. Now, that form wasn't in the original thing, especially since we just did. If it doesn't fit the criteria, you can't use it. But lo and behold, you really can use it here. This is a form they call a infinity minus infinity. And I wish they wouldn't even say that. Because what you have to do here is use subtraction of fractions to get it in a different form. And what would that be? You throw your stuff on the floor in disgust. Yes, that's what you do when you have a problem like this. So this would be the limit as x approaches 0. Now, you want to get this in a division form. So how do you do that?
So, you multiply?
Multiply what?
By whatever we use, was it x to the negative 1?
Okay.
I don't know how to get it back to.
Okay. What if you had, how would you do that?
Multiply by the reciprocal. Is that right?
Common denominator, okay? And what's your common denominator here?
Sine
x times sine x. If they have nothing in common, which 3 and 4 don't, what would be its least common denominator? 3 and 4?
Right, 12.
12. You just multiply them together. Same thing here. So you multiply, so I'm going to do it over here, x sine x. Okay. Now, what did I have to multiply this denominator to give you that denominator? X. So that would be an x up here minus sine x here. Okay. That form now, let's apply and see what we can do. See, all we've done is an algebraic manipulation, which is what we used to do with doing limits anyway, right? So, what does this give us if we plug in an x?
0 minus 0.
That's a 0 in the numerator and
0.
0 in the denominator, okay? I think that qualifies, doesn't it?
Yeah.
So now we do the limit as x approaches 0 of,
Cosine.
no, well, do the first.
Sorry, okay.
1
minus cosine x.
cosine x over, product rule.
So x squared, is it, no, I always get this wrong. Is it negative cosine?
Okay. Derivative of sine is cosine. So it's first times derivative of the second, so that'd be x cosine x plus, well, it may wind up, no, it won't wind up being, plus you did the first times derivative of the second plus the second times derivative of the first. Second is sine x, and what's the derivative of x? 1. Okay. So that's your derivative of the numerator and derivative of the denominator. Let's try it again. What do we get?
So 1 minus 1, 0.
0 over?
Over 0, 0. So
Again, so we'll have to try it again. The limit as x approaches 0 of
what's that? Sine x.
sine x, because derivative of cosine is minus sine, but you had a minus, so that makes it sine x over,
Let's see. Is it negative x sine x?
negative x sine x. That's certainly part of it.
Okay, and then just plus cosine x.
Plus cosine x. That's the first part.
And then the derivative of sine x is just negative sine negative cosine x.
No, it's just cosine x.
Cosine, okay.
So it's another cosine x, so that makes it plus 2 cosine x, right? Okay. Now let's take it again. Derivative of the numerator is 0, and the denominator is
0
plus
2.
2. So 0 over 2, that limit is
To infinity or undefined.
0 over anything is
0.
0, except in the fit. See, if that had been a 0 in the denominator, we'd keep going. When we wound up with a 2 in the denominator, the first term gave us 0, but the second term gave us a 2. Then it's 0 over 2, and the limit of 0 over 2 is 0.
That's right.
Okay, 0 over 2 is 0. Okay, and that's exactly what we write. So, what we had to do, so why did they even call that an infinity minus infinity? Forget that. Go and do what it takes to get it into a quotient form, which is what we did, and then start working with L'Hopital's rule. But every time evaluate and see if you've got the equivalent thing. 0 over 0 or infinity over infinity. We had 0 over 0 every time until we finally got 0 over 2, and that did it. Make sense? All right, that was example 7, if I'm not mistaken. And by the way, that is the graph of example 7. Okay? And this shows us if we were graphing any of these we've done before, including this one, okay? At the very beginning, we see that 0, this is undefined, that's undefined. So x equals 0, you're never going to have a value. You can have a limit, but you're not going to have a value. Remember, that's true about limits. So you're seeing if indeed this does have a limit. And sure enough, after doing all that work, you see the limit is 0, but it's not equal to 0 at 0, but the limit is x approaches 0 to 0. Both from the left and from the right. Stand out, sit down, 5, 5, 5. Okay. So it does work. Okay. And on every one of these, if you were doing a graph, if that first thing was undefined or indeterminate, let me say indeterminate, there's going to be a hole in the graph there. We don't know if the graphs even meet until we keep doing L'Hopital's rule. If you do come up with a limit and it's 1 or 3, what was that, 6/17 or whatever it was, it's going to be a hole at that point, but that's going to be what it's going to be approached from the left and the right. Except for that with the log, and that would be only approaching from the right. Okay. Blah, blah, blah. Okay. Limits of functions of the form of f of x raised to the g of x can lead to indeterminate forms, 0 raised to the 0th power, or 1 to the infinity power, or 0 infinity to the 0th power. Those are all indeterminate forms, as the limit can take on a variety of values depending on the relative speed with which the base and the exponent approach their limits. In such cases, we take the logarithm and apply L'Hopital's rule. Okay? So for instance, let me clear this and clear what I just did. Well, I think I went to the next slide, didn't I? Okay, which is probably what I need to, where I need to be anyway. Okay, so let's do this form. Evaluate this. The limit as x approaches 0 from the positive side of x to the x. Okay, now the reason that has to be approaching 0 from the positive side, when we did exponential functions, which was some base here raised to a variable base here, we cannot let the exponent ever be negative, because negative exponents and taking roots of those, they're just really wacko, because remember, you can't take the square root of a negative number, but you could take the third root of a negative number, you know. But what if you have a variable root, but it's negative? Don't go there. Okay. So keep the exponent always positive. No, keep the base always positive. I'm sorry, it's the base you have to keep positive. So that's the reason here. Yeah, you can have a negative exponent. The base can't be negative because that's what you're taking square roots or cube roots of. And if x is a variable, it occasionally could be even. Won't always be, but it could be. And then you would have indeterminate. I mean, it just is awful. So that's the reason x approaches 0 only from the positive side of the space can only be positive. Okay.
When you have a negative exponent, that's just another way of saying that's being divided. The base
It's 1 over x to the positive exponent. Yeah.
Cool.
Yeah. Okay. So what we do here is take a log of this. Okay. So let's pull this out and do I like to do it this way because it helps me go back easier. Let's call this thing here y. Okay, so that's how we're going to start. Let y equal x to the x. Okay, now x to the x is a very terrible form. Okay, so let's take a log of it, and that would give you log y is equal to, okay, it's log of x to the x. So our log y would be, and then what do you do? A log of something raised to a power. Do you remember that rule for exponents? Bring the power in front. x log x. Got it. Okay. So that's what we're going to do. Rather than take the limit of this thing, we're going to take the limit of that thing, which is exactly one of our earlier problems. So this is going to be, now remember, this is a different problem now because we got the log of it. Okay?
So we're going to set it up how
Yeah.
x has the negative 1
Yeah.
and get it in the denominator.
Yeah, we're going to do all that. So I think the best first step, that is actually the correct one, and I'm going to go in gory detail now. I think you'll see how to shorten this a little bit. That's the limit
Are you saying that basically we just memorize?
okay.
Since we've already established how to get from that to the end result. And
Okay. Here's what I'm saying. Okay. If this is y, what we're doing is the limit of y. Okay? Maybe that's how I should start. The limit, ooh, but we don't have a y there. Okay. If y is equal to that, then, like we just said, log y is equal to this, and that log y is equal to that. Okay? And what we're originally doing was the limit of the x, okay? Okay, so that would be the limit of y, and then we'll be doing, the thing is we don't know what the limits of this are, but just leaving that aside now, that's going to be the log of the limit of y, and I'm going to leave as x approaches 0 from the plus. I know there's no x in there, but okay. That's what we've done to this side. And what we have over here, this would be then the limit of, and just like we did before, x approaches 0 from the plus side of x log x. And we just did that, remember? That was our problem 4. Okay? That was the limit as x approaches 0 from the plus side of log x over 1 over x. Okay. Because 1 over x is x. Okay. You weren't here when we did that one, did you? Oh, you were? Okay, yeah. Well, then if you were here, I was thinking you weren't here yet. But when you do that, then you that gave you, like when we did before, minus 1 over x. When you carry that all the way through, because it's going to be 1 over x over minus 1 over x squared, which is that, and the limit of that is x approaches 0.
We rewrote it, x to the negative 1. That's how we took the derivative.
Yeah. Yeah.
And then we did, it was, negative 1 to the raised to the negative 2.
Yeah. But we wound up with 0 as the answer.
Correct.
Right. Okay. Because it's, yeah, I'm sorry. Yeah, that's right. It was 1 over that. Okay. And then when we did that, that would give you a minus x, and the limit of that as x approaches 0 was 0. Okay. But we want to take the log of 0 now. What's the log of 0? Because you see, we're doing the log of this thing, and this thing here was all that and that and that. So that, yeah. I think I'm saying all this right.
The form is exactly like an example 4. I just don't
Right.
see how where we're.
Well, okay. What we did was if you look, what they have written is very similar to what I did. The limit as x approaches 0 of log y, you know, down here, that's the limit as x approaches 0 of x log x, okay, because they did the same thing we did. Okay, so, okay, let me get my pen back. I don't know where it went. Oh. Okay. Goodness gracious, it won't come back. There it is. Okay. The limit as x approaches 0 from the plus, though we don't know what that is, of log y is equal to the limit as x approaches 0 from the plus of x log x. Okay. And we've wound up that this was 0.
Correct.
We did that. Okay. Now, we're looking for what are this limit over here. Okay. Now, how we find out what y is, okay,
Just out of curiosity, why are we trying to figure out what?
okay.
I know. I'm sorry. I know it's.
Okay. This has. Okay. Let's start from this. Just like we did. Let's set y equal x to the x.
Yeah.
Okay. So that log y is equal log x log x, right?
Okay. Yeah.
Okay. Now we take the limit of log y, okay, which is the limit of x log x, okay. And what we're wanting to do is find out what and that's what I was saying here. Okay. We found out this was 0, so the limit as x approaches 0 from the plus of log y is equal to this.
Correct.
Okay, we got that. All right, now we want to find what okay, let me phrase it this way. The log y, because log y was equal to this. Okay, so that's what so let's just write it that way. Log y is equal to that.
Right.
Okay, now we want to know what y is.
Okay.
Okay, so how do we get y out of log y? You take the exponential of both sides.
Okay.
E of log y is equal to e of 0.
Okay.
Right? E log y is what?
Is that just e log y? Or e to the x is just e to the x, so e log.
You're not taking the derivative.
Oh.
Remember that exponentials and logs are inverse functions of each other.
Okay, so they cancel.
They cancel each other, and that just gives you y is equal to
1.
Exactly.
Okay.
That's why you're wanting to go back. Okay, and that's what we got. Y, that would be 1. Okay.
I'm sorry.
yeah.
I'm sure I overcomplicated that, but I see what you're saying.
Yeah. Now, here is the graph of that function. Okay. If you had a graphing calculator, it had a graph.
Okay.
It's not defined here,
Gotcha.
but the limit is 1.
That's
okay.
the y-intercept. Yeah.
Yeah. The limit as x approaches 0 of this thing here is 1.
Cool. Okay.
Tells us that. Okay. Now, but only from the right. is not at all defined anywhere over here. And it's not defined to x equals 0, but it is, the limit does exist to x equals 0. Just the value doesn't exist there. All right, so that was example 8. Example 9 doesn't have a graph, a slide, so let's do that on this one too. Find the limit as x approaches 0.
Parentheses 1 plus 4x, close parentheses, raised to the 1/2 x.
It's 1 over 2x.
Right.
Okay. Not 1/2 x, but 1 over 2x.
Gotcha.
Okay. Because the x is also in the denominator. And that's the problem, folks. The x in this part is no problem at all. That's a 1. But it's 1 raised to the infinite power. Because as x approaches 0, 1 over 2x, 1 over 2 times 0, will be 1 over 0, and that's going to infinity. So that's the part that is outrageously too high. Yeah. So again, we want to find, we set y equal to this. Okay? Let y equal 1 plus 4x raised to the 1 over 2x. Okay? Anytime you have an exponential that's giving you problems, then take a log of it. Okay? So now the log of y is equal to the natural log of 1 plus 4x raised to the 1 over 2x. Okay? Now, so log y is equal to rule we just did.
Okay, so 1 over 2x.
Right?
Log
Times the log of 1 plus 4x. Okay. Now, we want to take the limit as x approaches 0 of both sides here. It doesn't make a lot of sense to do that for the left-hand side because there is a, so let's just do it here. So this is equal to the limit as x approaches 0 of log 1 plus 4x over 2x. All right. Now, what's that numerator?
0. The log of 0 is 0. Is that correct? Oh, excuse me. The log of 1.
Log of 1, yeah. The
It's
log
0.
of 1 is
0.
0 over 0. So that's a L'Hopital form.
Right.
So let's take the, yeah, that's the limit as x approaches 0 of,
Would you distribute out, so would it be a product rule?
no, this is a log function.
Okay.
And it's going to be a chain rule form, but it's a pretty small chain rule. It's the derivative of a log. We did it in example 4.
Right.
Example 4. Oh yeah, you're on a different, I was looking at where you were looking on the page. I said, that's not the right place. But yeah. Derivative of a log.
That's right. So you move it. Would it just be 1?
No, it's 1 over the argument.
Okay.
Derivative of log x is 1 over x.
Gotcha.
Okay, so derivative of this thing would be 1 over 1 plus
1 plus
4x.
Gotcha.
But then you have a chain rule.
So
Times 4. Derivative of 4x is 4.
Right.
So that's in the numerator then.
Yeah.
Okay. Over
Just
2.
2.
Exactly. This is looking a lot better. Let's see if it is. Take the limit as x approaches 0 there. What do you get?
So real quick, would you multiply by 2? You see how it's 4 over 1 plus 4x over 2.
Okay, I would plug in x
Just
equals
plug
0
it in,
first.
right, okay.
Yeah.
So
Yeah, okay, yeah, okay. I would divide by 2. Okay, you could do that.
Right.
Okay, if that's what you meant, yeah.
So
Hey,
Hi.
she came early today, this week. Got it, thank you.
And that other take-home test, I'm about to throw it. Just saying.
Oh.
I can't figure out half of it. I'm still on like number 9. Because I can't figure it out. I hate it.
You can.
No, I can't. It sucks. I don't like it.
the 2 over 1.
Okay, 2 over 1, which is 2. Okay, that's what log y. So log y is equal to 2, right?
I'm
And
going to go back, find out
e
y.
to the log y equal e to the 2.
Right, so
And
y
this-
equals e to 2.
E to the 2, that's right.
Perfect.
Yeah, good deal. A little louder, I can't hear.
What happened to the 1 plus 4x?
Okay. This right here, yeah. You plug in x equals 0, right? So 1 plus 4 times 0 is 0, so 1. So 2 over 1 over 1. Right? And you could have done there, 4 over 1 is 4 over 2, 4 over 2 is 2. Either way, you did it. That's how I was starting to do it, but he said, couldn't you divide out the 2? Sure, divide out the 2. But that all is log y, and then do your exponential to get e to the 2. Okay? Same type rule we did before. This looks a lot more complicated, but really doesn't turn out being that bad. Surprisingly. Now, they didn't show a graph of that one. Had they shown one, that would have been pretty ugly looking, or I would think it would be, but it still comes out as a whole in the function at x equals 0, but it's approaching e squared. Now, e is about 2.7 something another, so that squared would be something between 8 and 9, closer to 9 probably a little bit, maybe just right in between. So it's so that would be something like 2 squared would be, 2 squared would be 4, 3 squared would be 9, so this would be something between 4 and 9. 7. If you got a calculator, do e squared, see what it comes up to. 7. Okay. Yeah. Something a little bit more than 7. So wherever you have when x is approaching 0, this is a whole at 7 or 7.3 something. There's a whole up there. Okay. And how it gets there, I don't know. Don't know, but when it gets there, it's going to be there. All right. Now, this leads to, let's see, go to 11:10. Okay. Comparing the growth of functions. Sometimes we're interested in determining which 2 functions f and g grow faster. For example, there are 2 standard computer algorithms for sorting data, alphabetizing, ordering according to rank, and so forth. There's a quick sort and a bubble sort. The average time required to sort a list of size n has order of magnitude n log n for quick sort and n squared for bubble sort. Which logarithm is faster when the size of n is large? Okay? So the question is between n log n for quick sort and n squared for bubble sort. Okay? Now, to me, it seems like this is a no-brainer, okay? And I may be completely wrong on that, because what n squared is n times n, and this is n times log n, okay? If n is a very large number, because of the nature of a logarithm, it comes up and it doesn't level out, but it goes up very slow. Whereas n log n, it goes up linear. So as n gets very large, it looks like to me bubble sort's going to be by far the bigger number than n log n. So it looks like quick sort. Is that what they get here? Okay. Okay, here it is. X is a great deal less than G. Yeah, alpha of X is a great deal less than G of X. That's what I was thinking. Well, we'll see. Okay. Anyway, that's the setup. Let's go on to theorem 2. Okay. Theorem 1, I guess, was L'Hopital's rule, wasn't it? Yeah. And here's theorem 2. All right, L'Hopital's rules for limits at infinities. Okay. So the alpha of x and g of x are differentiable functions, got to be, on an interval from b to infinity, such that g prime of x is not equal to 0. The second one, that derivative is not equal to 0 for x is greater than b. It could be for x is less than b, but not for x is greater than b, because that's where we're looking, x greater than b, from b on. Then the limit of alpha of x and the limit of g of x exist if the limit as x approaches infinity of alpha of x and the limit of as x approaches infinity of g of x exists. Now what does that mean? As x is going to infinity, alpha of x has to have a limit. Okay? Somewhere out there, there's some value that never gets any more. Same thing for g of x. And either both are 0, or both are infinite. The limit of alpha of x and g of x exists. To me, that sentence doesn't make any sense. If the limit as x approaches infinity of alpha of x and the limit as x approaches infinity of g of x exists, okay, and either both are 0 or both are infinite, okay, what are you talking about both? The function or the limit? If the limit, I guess they're talking about the function, because they've already said the limit exists, and if the limit was infinity, it wouldn't exist. So they must be talking about the functions. Yeah, they have to be. It's not really clear. I think they'd be a lot clearer if they put both alpha and g are infinite. Either both alpha and g are 0 or both alpha and g are infinite. Okay. Then the limit as x approaches 0 of alpha of x is the same as if we did for L'Hopital's rule. Before L'Hopital's rule was x is approaching some value a, now it's x going to infinity. If the functions are differentiable everywhere, and they got provided that the limit on the right exists. Okay, so this limit does exist. Okay, similar result holds as x approaches negative infinity. Okay, a lot of blah blah blah. Let's actually use it. So example 10. I think this is example 10. So let's do it. Which form of f of x equal x squared? Now, this was blowing my mind. If you look up at the top part, they had f of x equal x log x and g of x equal x squared. And now in the example, they flip them. And it was just driving me crazy. I thought we just assumed the other way. Okay, but we're okay now. G of x is equal to x log x. Exactly backward of how they said it before. But this, forget about before, this is what we're doing now. Which of these grows faster as x approaches infinity? Okay, so what we're looking at is what the ratio is. Okay, we look at the limit as x goes to infinity of, and we're going to do it the way they said here, not the way they said above, x squared over x log x. Okay. Now, x squared, of course, is x going to infinity, that's going to infinity. X log x is x is going to infinity, that's going to infinity. So neither one of those exists the way we have done before. But L'Hopital's rule theorem 2 says we can take the derivative just like we did before. So this would be the limit as x approaches infinity of 2x. And do you remember what that one was?
X over 1 over x, negative x, to raise the
Okay.
negative 2.
Okay.
Sorry, I was just looking back to the
Okay.
example.
Yeah, we're taking the derivative of that thing. And I don't think we did that before, did we? We took the limit separately, or derivative separately, or did we?
Well, we took the derivative of it,
And what is it?
or we took the limit as x is approaching 0 from the positive, which doesn't really matter. I'm just
Right.
looking
No,
at
yeah, but that's a different problem. Here we're just taking derivative of this.
Okay.
Derivative of this is a product rule. And that would be what?
Is it not? Well,
Just going to say, you may be right.
well, that's what I'm saying. Is it not x raised to the negative 1 over negative x?
Okay, no. Okay, you're doing the limit of this thing. We're not doing the limit of this thing. We're doing the derivative of this thing.
Sorry.
Yeah. So what's the derivative of x log x? Say again? Okay, x times 1 over x, because x times derivative of the second, first times derivative of the second, derivative of log x is 1 over x. So x over x, I know what that is, plus log x, isn't it?
Yeah.
Log x times derivative of x, which derivative of x is 1. So this is, that's 1. Okay, so I won't have to write it again. Now take the limit of that.
Still infinity over
Infinity over infinity. So let's do it again. Limit as x approaches infinity of 2 over 1 over x, isn't it? Which is 2, okay. The limit as x goes to infinity, well, let's do it this way.
multiplying
2 times
infinity.
x over 1.
Right.
and that would just be infinity. Okay, so the limit of those, so who wins? The top one wins. The top one is the bigger. Okay, what was the question? Which of these grows faster as x approaches infinity? The f of x does. And here's the graph of it indicating that. By all means. And I mean, it sort of makes sense because this is x times x and this is x times log x. X goes like this, x goes like that, so x squared goes like that. Okay, we know that. X goes like this and log x goes like this. And the product of those has got to be less than the product of this. Okay, yeah. So f of x grows faster. Okay. And that drove me nuts because before we arrived, they switched the f and the g, and I thought, we got it backwards before. No, we didn't. They switched the f and g before. So that, sure enough, is going to infinity. So we conclude that x log x is a great deal less than x squared. So that implies that the quick sort is much faster sorting a logarithm than bubble sort for very large n's. Now, frankly to me, it seems like it's for very small n's too. Look at this. It never is, this is always greater than this. Of course, this goes negative here. I don't know what it means for that to be a negative number. So maybe between 0 and 1, that's better. I don't know. We won't go there. Okay. Do we have time for example 11?
We have 3 minutes.
Let's try it. Okay. Let's see if there's any. Yeah, maybe so. Okay. Jonathan is interested in comparing two computer algorithms whose average run times are approximately log n squared and the square root of n. Okay? Which logarithm takes less time for large values of n? Okay? Now, why they choose to put what over what, I don't know. I guess they do it this way. What they're looking at is the limit as x approaches infinity, because that's taking the place of n. X approaches infinity, getting to be a very, very large number. And why they put the square root of x on top and log x squared in the denominator.
I guess from not having to make, put the square root and the number. You see what I'm saying? By already doing it, you don't have to do it. I don't know.
Okay. The I can't tell right off the top, except I think maybe what you're saying is that's going to, that's going to get messy.
Right.
The denominator may or may not be as messy.
Right.
So that numerator is going to keep getting larger. So anyway, they did it this way. So we're going to see which algorithm takes less time. They put the square root of x on top. Now, of course, if you let x go to infinity, the numerator is going to infinity, the denominator is going to infinity. So both of them are differentiable, so let's use L'Hopital's rule. What would that give us?
1/2 x raised to the -1/2.
Okay. 1/2 x to the -1/2. Perfect. Over.
Would you factor? How would you tackle that? Would you go ahead and factor
Okay.
it? Or
I wouldn't. I would just take the root of.
So could you do it 2 log x to the -1 or to the 1? Oh, okay. So
To the 1, yeah.
Over x
Times the root of log x. Okay. Now, let me rewrite that. Limit as x approaches infinity of, this will be a 1 over 2 times the square root of x. I'm going to go back to the way it was, but that's what that means. To me, that's easier to evaluate than this. And this will be 2 log x over x. Okay, now plug in an infinity there. What's the numerator heading for?
Infinity?
No.
Wait, would that still, or
The x is going to infinity, square root of x is going to infinity, 2 times the square root of x is going to infinity, but 1 over an infinity is going to 0.
Okay.
Okay, so that numerator is 0. How about the denominator?
Infinity. Is that infinity over infinity?
Yeah, it would be.
Yeah.
So it looks like what we have to do.
Didn't we have a rule for 0 times?
Yeah, but 0 divided by anything. But we don't know who's winning in the denominator is the problem. It's an infinity over infinity. So what we need to do is keep working on the denominator. We already know the numerator is going to 0. And the denominator, if that's going to 0, then it's 0 over 0, and that's indeterminate. If the denominator is anything else, that's going to 0. So you've got to figure out what that denominator is doing. So let's take that another step, but only deal with the denominator this time. The limit as x is approaching infinity of 2 log x over x. And what would that be?
Whoa. Are you saying that you can take L'Hopital's rule on just one?
Okay, no. We have a limit. Okay.
Sorry.
We know that this, as x goes to infinity, is going to 0.
Right, correct.
We don't know where this one's going.
Okay.
So that's what we're doing now, is seeing where is that going.
Okay. So we're able to take L'Hopital's rule on that?
Okay, yeah, we can do that because that's an infinity over infinity.
Cool.
Okay. Now what does that give us? Okay.
2 log x. So x.
It's
2 log?
2 over x. Right? Because derivative of log x is 1 over x.
Right.
So 2 over x.
Over 1.
And what that's going to?
Infinity.
2 over infinity is going to 0. So this is going to 0. So we're back to that one. Yuck. Okay. All right. So let's go back. Yeah. So now we go back up here. The limit as x approaches infinity of, let's go back to this, 1/2 x to the minus 1/2 over 2x to the minus 1.
Okay. Gotcha. I see what you did.
Right. And that's going to give us a 0 over 0. So let's do another derivative. That'd be the limit as x approaches infinity of, take the derivative again,
Break it down. So what, x to the negative?
negative 1/4 x to the minus 3/2 over
Negative 2 x to the negative 2.
all right. Now, what have we got here? This will be a minus 1 over 4.
Square root, cubed root, right?
No, it's the square root of x. I don't have to put this in. Square root of x cubed.
X cubed, right?
Right. Over minus, and the minuses can go out, 2 times 1 over x squared. Okay. Now, these are exponents you can play with. Okay. Number one, your variable is 1 over 8, right? And what we have is, let's do it this way, x squared over x to the 3/2. Because the minus that's in this down here is the button up there. Okay, so you got that, and what is this going to then? This is x to the 4/2, x to the 3/2. This becomes x to the 1/2. So you have x to the 1/2, x to the 8. Now the limit of that, as x is going to infinity, this is infinity over a number. So that's going to infinity. We can stop right there, okay? And this wasn't this problem here, was it? So what does that tell you? That limit, that one's the bigger one. Okay, the square root of n. Yeah, ultimately you get to infinity. That shows that the square root, that the 1 over the log of x squared is a great deal less than the square root of x. And so therefore that first one is the smaller one. We conclude the algorithm whose average time is proportional to log n squared is less than for large n. Yeah, that's what we got to. Okay, we are through for today. Sorry, we ran a little over. Now, what we had decided to do last time, we did, let me give you homework exercises first, okay? Any of the odds 1 through 9, any of the odds 11 through 15, and any of the odds 17 through 53, okay? And if I were you, I would probably stop there, okay? Boy, I wish we had time for graph sketching and asymptotes, but it doesn't look like we're going to get there. Applied optimization, I wasn't going to do that anyway, even though those are fun exercises. I did want to do Newton's method, or at least show it to you. So that's as far as we're going to go in actually, we'll start with Theorem 3 and just show it to you. That's all we'll do, okay? And then we will, I'll just do some very quick slideshow of 4.6 because it is important for you to know, though I won't test you over it, but it's stuff we've already done, okay? But it is just doing that. So we will start there. And then we'll skip 4.7 altogether. And now again, I'll just do you a slideshow on Newton's method just so you get to see what a beautiful technique that is, okay? And that ends the chapter. And so I'll do that hopefully pretty quickly next time. You won't be responsible for anything past what we did today. You'll need to know it when you get to the next level, but I'm not going to test you on it. But I did want to at least introduce you to the integral. And we probably won't have time to do as much as we should do, but we will get as much as we can done on the integral next time. And what little bit, we'll see how far we get, and that's as far as I'll test you. The trouble is, I've got to make up the test before this, so I've got to figure out how far I think we'll get. But if we get further, if we don't get as far as I think, then any questions that from that will be beyond where we cover will be optional. So I'll give you the test, but I won't make you do any that are beyond what we get to cover in class next time. So I have the test ready for you. Knock on wood. I've got this much grading to do, and I've got to finish fall schedule. Pretty close to finishing fall schedule, but they piled this onto us right at the end of the term. I've been looking every week for the last month or so to work on fall schedule. They never opened it. And last week they opened it and said it's due by next Tuesday.
Serious.
And so, yeah, seriously. So I should have worked on it more this weekend. I got some done, but not as much as I should have. But it was a really rough weekend, so I didn't. So anyway, we'll get as far as we can next time. I'll have the test made out for you. We don't get as far as I thought we would. Any past questions will be optional. So we'll do it that way.
You'll have us our test ready, and we'll have you our